Okay, can you all see the screen first of all?
Yes.
Excellent. And by the way, can you see my video as well in the top right-hand corner?
Yes.
Great. Okay, so I just wanted to make sure you're looking at the same thing. So what I'm going to cover today, there's a few people coming in, so I'll just admit them as they come. Hello, Farah. We are literally just starting now. So I was just explaining, please ask questions as we go, because I won't be able to look at the chat, but you should be, you can unmute yourself and ask a question. So today I'm going to talk about objective reality. So first of all, what it is, which is just simply amazing. And then how we've got there with the mysteries are the incredible, amazing forces that happen at the quantum level. So we all know quantum physics, and quantum physics again is just the study of anything subatomic or even atomic. But so scientists 100 years ago, when they got the ability to look inside an atom, they could not believe what happened. And you'll see, we'll talk about that sort of stuff lately. So I'll tell you what objective reality is, and I've got a short video on that. But then I'm going to really get into these amazing experiments and what they mean and what they've shown us. The double slit experiment is part of everything in quantum physics. It shows us superposition, which I'll explain. And then there are two important points which I'll go over, and that's the observer effect and the measurement problem. And today we'll be focusing on the measurement problem. I mean, the observer effect, we could talk for months about it. It's unbelievable. But the measurement problem, and I know I've got one computer scientist in the audience, Aritra, who is doing some amazing stuff in quantum computing. The measurement problem is like Aritra. We always say, if you measure the qubit, and the qubit is just the unit of a quantum computer, as a bit is to classical computers. When you measure the qubit, it collapses to 1 or 0 with equal probability. Now, you probably just accepted that as that's what it is, but it comes through the measurement problem, and it'll be great for you to see behind that. The delayed choice quantum eraser experiment, which I have done in previous presentations and will do again, shows that at the quantum level, time doesn't exist, but it also feeds into the measurement problem. But it actually shows that events that have already happened can be altered. Amazing stuff. It's all amazing. Then we have the Radin experiments, which talks about consciousness. Because the measurement problem is, when is that measurement made? And we still don't know. And there's still a lot of conjecture, even though this latest experiment from the University of Edinburgh seems to have the answer, yet there's controversy about that answer as well, which I'll get into. There's always controversy in quantum physics, and I'm not here telling you what was right. I'm here telling you, one, exactly what happens in these experiments that are all scientific. There's nothing spiritual or mystical going on here. This is science. The experiments have been conducted and reproduced thousands of times. The double slit hundreds of thousands of times. And what happens always happens. It's never ever failed. Quantum physics is alarmingly, amazingly accurate, far more accurate than Newtonian and classical physics, which is gravity, electromagnetism, radiation, which is the weak nuclear force, and the strong nuclear force, far more accurate than any of them. But I'll explain to you Wigner's friend, and that was Eugene Wigner, was a theorist in 1961. He said, what if while someone is observing the wave function, and I'll explain what that means during the course, but what if someone's observing the observer? Can there be a remote observation and a local observation? And in point of fact, that's what we've now reached, the technology that we can do that. But when we compare them, there are conflicts, there are contradictions. There are contradictions, which is amazing. Because that means that one person's reality is different from another person's. So, unbelievable. Forkinger and Renner, it's basically a white paper backing all of this. And I've also got a list of all the references. But look, what I'm going to do now is take you through, where do you go? Okay, just give me a second to get back up. Okay, could we all see that video just to make sure?
Yep.
Yeah, excellent. Thank you. The important thing from that, besides all the amazing stuff, is that what this experiment that she was alluding to, that I'll go into, which is from the University of Edinburgh, by Massimilliano Proietti, an Italian, I assume. What he's proving is that if someone's observing the observer, then it all becomes one great big superposition. And if it's one great big superposition, then different people remotely and locally measuring it will have different results. And that's what happens. Oh, shouldn't be the measurement problem, yeah? Okay, so I'm going to go all through the measurement problem. Now, first of all, the double slit experiments. I just want to, I'll go over this quickly because I think most of us know it, but it is the pivotal experiment in quantum physics. And it goes back to 1801 with Professor Thomas Young. And he actually, through curtains, he shone a beam of sunlight aimed at a detector with two slits in it and a back detector with where they would, where he could have a look and see what the pattern was detected at the end in the back detector. Because he knew what they were trying to find out in 1801 was whether light was a wave, like water or sound, or a particle, like a particle, like a bullet from a gun. And by shooting it through two slits, if it would have been, like, imagine you had a machine gun firing at those two slits, the back detector would have two vertical lines, and that's called a clump pattern. But amazingly, what happened is the back detector had many vertical lines, the strongest ones in the middle, and that showed to Professor Thomas Young that light was a wave. Because imagine if you pushed water through two slits, the waves would interfere with each other and they would touch the back detector in specific places, causing many lines. And that many lines is called an interference pattern. So if you see an interference pattern, it's a wave. If you see a clump pattern, it's a particle or a bullet. Now, for 100 years, Professor Thomas Young said, hey, everybody, I've solved it. Light is a wave. And for 100 years, that is what they believed. Until this man, who you may recognize, Mr. Einstein, he came up in 1912 with his, in fact, the white paper that he received a Nobel Prize for. He didn't get a Nobel Prize for his special theory of relativity, like time dilation, which is brilliant. I've done another presentation on that. And general relativity. He got it for this. And it's the photoelectric effect. Now, what it proved, I won't go into it, but what it proved was that the electron or the photon, the subatomic particle, was a bullet. It was a particle. It wasn't a wave. And Einstein said, look, I'm not saying Professor Young is wrong. In fact, he's right. I've done his experiments myself. But this new experiment shows that light is a particle. So, wow, it absolutely confused the scientific community. They had no idea. And then about 20 years later, they had the ability from an electron beam gun to send through, it's actually a photon rather than an electron. It would happen with any subatomic particle. It doesn't matter, electron, photon, photon has polarization, an electron has spin, doesn't matter. They both, any subatomic particle, a muon, taion, fermion, hadron, anything that goes through the double slit will have the same thing happening. And what was amazing was that they got to the ability where they could send one photon at a time, and they thought, oh boy, we've got to find out what's happening here. So they placed a camera, not one like that. That's my poor graphics capability. It was a laboratory camera, highly sensitive camera, to look at what happened to the wave or the particle when it went through the slit. And an amazing thing happened. What they found was that, sorry about that. what they found was when the camera was on, if you can see at the, I'll actually do some annotation here so you can see me. So when the camera was on, the back screen detector was a clump. And as soon as you moved the camera away, it became a interference pattern. And I literally mean turn the camera off, it's interference, turn the camera on, and it's a particle. And we could talk about this literally for days, but what that proved beyond doubt was that the subatomic particle is in a wave function. It's in a superposition. Just like on the video, they said, you know, the electron doesn't orbit the nucleus like we've been taught. You know, like the Earth goes around the sun. It's not like that. It's like a huge, mulled up, confused cloud of probability, which does form a wave function. And we can predict that wave function with Schrodinger's equation. And we can also work out the probability of the electron being at any stage in the wave, at any state in the wave function through a thing called Bohm's rule. Aritra, you will know Bohm's rule as the absolute value of the complex amplitude coefficient squared. And now you know a bit more about what it's referring to. It's referring to the probability that the electron is at a certain point in this strange cloud. But as soon as you observe it, now this is the observer effect, as soon as you measure it, as soon as you observe it, wrong word, but never mind. As soon as you observe it, it stops being a wave and it becomes a definite point, a definite particle, a thing. It's amazing. Theologically, one can extrapolate that to mean, was the first thing ever created observed by a conscious being? So it gets very theological, epistemological, metaphysical, and all those things. So it's amazing, but immediately it's a clump. As soon as you put the camera there, it's amazing. Do we have any questions on that? Okay, can someone just say hello? I want to make sure you're listening, you can hear.
Hi.
Yeah, thank you. Okay, look, there shouldn't be any questions on that because it's, you know, I'm only skimming the surface, and I have done other presentations that focus on that, and I will do again. But that's, oh, someone's sharing my screen. Yes, and please continue to do so, I don't care. Okay, so it seems like if we measure the subatomic particle, it changes from a wave function to a particle. And that's called wave-particle duality. It's both. It's something that doesn't exist in the classical world that we live in. And may I say straight away, a lot of students say to me, oh yeah, but this doesn't happen in the real world. And I always stop them, The real world, the fundamental law of the universe is quantum mechanics, quantum physics. That's the real world. Our world that we can see, feel, touch, and live in is an emergent condition from the real world. So, yeah, our world is not the real world, if you like. It's an emergent state of affairs from quantum physics. So it's amazing, but we don't have words to explain the quantum physics because it's so different to what we're doing. But people were saying, now hold on a minute, when you measure it, you're sending a light signal which will hit the subatomic particle and it will change its where it's going and all of that. And scientists said, well, fair point. Doesn't quite explain why it would collapse to a clump, but fair point. And then the DCQE, which is the delayed choice quantum eraser, which is basically the double slit with entangled particles. Now, entanglement is another property of the amazing quantum world, where you can have two subatomic particles. When they're entangled, they go, you could put one on the moon and one here, and when you change the one here, the one on the moon changes instantly. We're talking about something a million times smaller than a speck of dust. So how something on the moon, the size of a millionth of a speck of dust, knows that something in the laboratory has changed is beyond all comprehension. We don't know. I might add, quantum computing doesn't know how we do it, but quantum computing actually can harness the superposition and the entanglement very easily by using complex numbers and imaginary numbers, because the wave function's like imaginary, but it's amazing. But the delayed choice, if you look at the second point there, the delayed choice quantum eraser experiment, the middle point there shows that just by knowing the path, so not by measuring, not by anything, but just by knowing it, will collapse the wave function. And here's the delayed choice. I would love to spend the next couple of hours on this, but time doesn't allow me. But what I might do is get my annotation out again. And what I'm just going to quickly show you is that here's the double slit, and when the subatomic particle goes through, it's immediately entangled. So it creates two entangled particles out of the one particle, and it sends one way and the other way. So we could look at the red. If you look at the red, that goes that way, and it's an entangled particle, its entangled twin goes another way, and then it hits a thing called the beam splitter, so it might go up there, or 50% of the time it will go on. It will then hit another beam splitter, 50% of the time it goes there, 50% of the time it goes here. Now the important point, and I can't go into it, I wish I could, is that the first entangled particle gets to the detector here. I'll put the spotlight on. So the first entangled particle gets here before its twin has gone through this series of mazes and reflections, i.e. we don't know where it's going to end up. But where it ends up is going to be either, if it, for example, ended up, let's just say it ended up here at detector 4. If it goes to detector 4, it could only have come from the top slit, i.e. we know which way it went. And therefore, at detector 4, it will be a clump pattern. Now, amazingly, what will show up here at detector 0 is a clump pattern. So this travels here quicker than its entangled brother or twin travels here. Yet this one always is a clump if its entangled twin goes to D4. But if the entangled twin, 50% of the time, it will go through the beam splitter, hit the mirror, and go and bounce. Oh, I'll go this way. Go through the beam splitter again and land at D1. But at D1, it could also have come from the blue. It could also have traveled that way. So we don't know which way, because it could have come from the top or the bottom. And what that means is that here at D1, it'll be an interference. Now, if that happens, there'll be an interference pattern at D0 somehow. So somehow, somehow the subatomic particle here knows what's going to happen to its particle twin in the future, or somehow the entangled particle twin somehow rewrites, goes back in time and rewrites it's like saying, look, I'm going to go through the beam splitter, but on the second beam split, I'm going to be deflected. So you better change what you've got from an interference to a clump, or from a clump to an interference. So it's just absolutely amazing that should happen. But again, it's showing us that if something is stopping us from knowing that, we have the technical equipment to look further into this, but every time we try to look at it, somehow nature knows we're trying to measure it, and it stops the wave function and it becomes a particle. And that's just inconceivable. Now, the measurement, so the observer effect is that when we observe it or measure it, it completely changes from a wave function to a particle. And one of the greatest theoretical physicists of all time, John von Neumann, he said, look, when is it being measured? I might add, Einstein just didn't believe any of it. He had to be shown it time and time again. And then he famously called it spooky action at a distance, and God doesn't play dice, because he could not believe that the universe was probabilistic as opposed to deterministic. Because when you measure the wave function, it collapses to its eigenstate, which is either 1 or 0 with equal probability. So the universe is probabilistic. Einstein could not accept that. He said, no, there's something we don't know. And I could go into that for hours, because there's a whole history of what happened. And then John Bell proved him wrong. But let's just stay with John von Neumann. And he said, where is the system? When is it being measured? Is it when the observer, is it when it's on the photographic plate? I'll put, sorry, I didn't mean to do that. I'll annotate again so you can see what I'm talking about. Okay, so John von Neumann said, when is the system being measured? Is it at the photographic plate? Well, that was immediately not true, because if you had and Einstein said this, he said, are you telling me that a a subatomic particle can empirically, fundamentally change its form depending on whether someone's looking at it. Are you telling me if a 5-year-old looks through that camera, that it will change its form? And the long and short of it is that no, a 5-year-old couldn't, because the 5-year-old isn't conscious. So von Neumann said, a physicist will collapse it because the physicist knows he's doing a measurement, whereas a 5-year-old's just looking around thinking what he's going to get for lunch. So it's not at the photographic plate, and then is it at the eye of the observer? And that proved not to be the case as well. Is it at the brain? And von Neumann said, no, it isn't. Is it at the mind? And it can't be at the mind either, because then the delayed choice quantum eraser showed that it's not at the mind, because just by possibly knowing the root of it can collapse the wave function. So when is it, John von Neumann suggested, that it is, this is how he termed it, this is Professor Radin, by the way, but John von Neumann, just go back in for a second, John von Neumann said, when the measurement takes place is when it reaches what he called an external physicality. So not a human, because a human is a quantum object. So he was saying, if any object don't forget, every object is a quantum object because we're made up of subatomic particles. So he's saying, if it's true quantum objects involved, then they become their own superposition. A quantum object can't collapse the wave function. So he's saying none of these things collapse the wave function, but somehow when it reaches the consciousness of a physicist who knows what he's measuring, so when it comes to the consciousness, that's when the wave function is collapsed, which is amazing, because that means there's a thing called, Kristen will know this, there's a thing called micro psychokinesis, which is the projection of consciousness external to the body. Now, he's saying, I'm not saying he's right or wrong, but his interpretation, and von Neumann is like Einstein in the quantum physics realm, he's saying that consciousness somehow is projected and affects an external object. And I just wanted to bring in Professor Radin, who I've followed since 2012, and he has compared meditators who are in touch with their consciousness, because if it is conscious, he's tired of people talking about it, so he's trying to prove its consciousness. And he got meditators in, and they were much better at collapsing the wave function, and he did it in different countries. And he's got all the results, and he's reproduced those results. But it's still not accepted by the scientific community. He was literally knocked back in February of this year, 2020, but he's not giving up. And they knocked him back simply because they're saying, we don't know if there's more to it, if you like. And I obviously could talk about this for hours and hours, but there's one thing I want to say. He had meditators doing it over the internet. So a light would come on and they would imagine the subatomic particle going through one of the slits. And then if they could imagine that, it could collapse the wave function through their hyper consciousness. But what he did it over the internet, so they were 4,000 miles away, but then he wrote a Linux program that simulated the data coming over the internet. So it's a simulation. You can't tell one from the other. However, when there was a human being at the terminal, it collapsed the wave function far more often than if it was just a Linux simulation. So fascinating stuff. But now we're getting to the main stuff, and I'm just going to check. I'm going to take about a quarter of an hour on this, and that'll bring us roughly to 8 o'clock, and then I'll take questions. Wigner's friend. So, Eugene Wigner in 1961, with all this, you know, when the measurement problem, i.e., when is the measurement being made, and the observer effect, and what is collapsing the wave function, he came up with, well, what if I have a friend and I tell him I'm going down the shops, and I put him in a laboratory and I get him to collapse the wave function to 1 or 0, and only he will know. But Wigner observes the observer. So here, the last minute he thinks, hold on a minute, I'll observe my friend making the observation. Now, this gets back to now quantum objects, sort of, if you like, it's a bit like a Russian doll. You keep taking a doll out of a doll out of a doll. So what Wigner was saying was that when someone collapses a wave function, they become, to another observer, a remote observer, in this case Wigner, they become in superposition with each other. So the whole laboratory, the whole thing that Wigner's looking at is in superposition, even though Wigner's friend has already collapsed the wave function. So he was saying, if you observe the observer, and then someone could observe the observer observing the observer, it just carries on going, and can you get different results? I.e., Wigner's friend could collapse the function to 1 with a 50-50% chance, but Wigner himself could look at the whole situation that his friend is superimposed, is in superposition with the box, and Wigner may come to a conflicting, he may see it as 0, because he's independently collapsing the wave function. Now that all sounds strange, and it sounded very strange 60 years ago, and it's never been proven until 12 months ago by Massimilliano Proietti. And that's Massimilliano on the left. And by using 6 pairs of entangled photons, he proved that, let's say, go back to Wigner and Wigner's friend, although I'm going to add another twist. But he proved in an experiment, a scientific experiment, using entangled photons, he proved that Wigner and Wigner's friend could have conflicting results. And that means the wave function could collapse to 0 for Wigner and collapse to 1 for Wigner's friend, which is inconceivable. It proves, if you like, although there's conjecture, as there always is, but it means that someone's reality is different from someone else's reality. Wigner's friend reality is, oh no, it's collapsed to 1. Wigner's reality is it's collapsed to 0. that fundamentally shows that in our one universe, you are part of writing your own reality. Because how you choose to measure or observe the subatomic particle dictates what your reality is going to be. I hope I've explained that quite well. Here's how he did it. So he basically had photons, and I'm not going to go into this in too great a detail because it really would take a long time. But he has them, he has one laboratory. So instead of just having one witness friend in a laboratory, he has two, and they're all entangled. So if they're entangled, they should have the same outcome. So he had Alice's friend examining, I'll take my annotation so you can see where I'm going. So here is an actual photon, which is polarized vertically or horizontally. You know, like polarized sunglasses, light is polarized. And so the photon is measured by Alice's friend in a box, like Wigner's friend in a laboratory. So same thing, it's measured here, and then Bob measures it here, and then Bob outside makes a decision to actually measure the photon at source. So he might measure it completely himself, or he'll measure what his friend, who's in superposition in the box, he will measure what he will collapse that superposition. And the same on this side. Now, the twist I was talking about is that Alice and Bob are not human. And this is what Massimilliano's done that no one else has ever done before. He's actually using photons to measure other photons. So there's no consciousness involved, there's no human involved. A photon is measuring a photon in here. I can't quite remember what PBS was, will be photon something. The photon is measured by another photon, and the measurement recorded on another photon. So now, is that a measurement or isn't it? And this is the conjecture. Massimilliano is saying that it is a measurement, and then he proved that over a period of time, which proved over what's called, it violated what's called Bell's inequality, which just means it mathematically, statistically proved that the outcome from the outside the box was different, conflicted with the inside of the box. So, and Massimilliano, he detected it using an interference pattern that is really an interference measurement that it has only been available for about a year. Before that, you couldn't tell whether a combination of particles were in superposition or not, but now you can. And so going through that, he has proven that at a quantum realm anyway, somebody remotely, like this Alice and Bob here, has a different reality to somebody locally. And that changes everything we know about reality. It really does. Here are my research references, and I'll give you a copy of this presentation and the slides. And there's all of the latest stuff, the latest papers and everything. And that is the presentation. So guys, I hope you followed as much of that as you can. It's crazy stuff, of course. And I'd love to take some questions.
Eamon, hey.
Hello, Chalet, is that right?
Hey. Yes, absolutely right.
Where are you from, by the way?
I'm from Turkey.
Oh, Turkey.
Yeah. Have you been there?
Oh, I wish I had been there. No, I haven't. But funnily enough,
okay.
I was on a global KISS, which is an IBM summer school.
Yeah, I attended that too.
Oh, you attended it too? Oh,
yes.
Look, please keep in touch, okay?
Sure, yes, I would love to.
Yes, I was in touch with a chap and a woman from Turkey all through the course, and we were sharing notes and everything, and it's wonderful. So I love that.
Great to hear that.
Yes.
Sure. Thank you very much for the presentation. It was a mind opener for me, actually.
Yes.
And
thank you.
My question will be about the double slit experiment.
Excellent. Yes.
Isn't looking at the output, the wave pattern or particle pattern, isn't it considered as an observation in this context? Yeah,
look, great question. And I will say what I always say, the words are wrong. Don't think of observation, measurement, that there are many words to say what's happening, but we don't have a word that can truly explain what's happening. So it's observer effect is now, you know, it's become the term. But it's not observation, because a 5-year-old may look at it, but he won't collapse the wave function. It's something much more than observation.
Okay. And because I just want to be sure, we are saying that the electron chooses both slits if we don't observe it. Is it a reality, or is it because our inability to observe it accurately?
No, thank you again. Great question. We have the technology.
I can open my video.
We have the technology to be, we have the technology to be sure of what we're doing. Nature is preventing us. When we put that high speed camera on the slit, nature changes it immediately. Honestly, and I know this sounds pseudoscience, but this is not pseudoscience. This is what happens. If you have a camera there, then the pattern at the back detector becomes a clump, and it happens every time. We are not allowed to know, and I don't know whether you heard of Heisenberg uncertainty principle.
Yes.
Yeah. So. Heisenberg said that Werner Heisenberg, great bloke, big wig, said that with a subatomic, in fact, he started all of this off by saying, we cannot know the momentum and the location of a subatomic particle. And that's essentially what's happening here. When we try and know both of those things, nature stops us. And it's not our fault. And the delayed choice quantum eraser further proves that just by possibly knowing, we're prevented from knowing. I don't know whether you followed the delayed choice quantum eraser, because
yes, I've also read it in a book named Through Two Doors at Once, I think. And I was familiar with that, but I should read on more to comprehend. It's a little bit complicated for me.
Look, it's complicated for everybody. It's only 20 years old. It was only 20 years ago that this was done. And the other experiment is just 1 year old. Hi, Kristen.
Yeah.
So
Hi.
it's, it's just, we don't have answers for this.
Yes, maybe someday we will.
Well, the important thing is, scientifically, this is what happens time and time again. And then we have interpretations. John von Neumann's you probably heard of John von Neumann as well. He's an amazing guy. It was John Wheeler who worked with John von Neumann. John Wheeler actually created the term black hole. And in fact, I don't want to digress too much, but what they showed is if you've got light, a photon coming from a distant star, how we choose to measure it now dictates whether it's been a wave or a particle all the way for the 10 billion years it's traveled. So it may travel 10 billion years as a particle. But when we view it, instead of directly viewing it, so we don't know which way, we put it through what's called an interferometer. And that's the interferometer measures gravitational waves. LIGO and Lisa, what's about to happen. So if we choose to measure it that way, it will actually, well, this is a Gedanken, it's a thought experiment, it's not science. But he said, if we measure it that way, it means it will have traveled, it thought it was a particle for 10 billion years, but actually it was a wave. So yeah, I mean, incredible stuff. But the great thing, which the wonderful Aritra would tell us, is we're building computers using this, harnessing these forces. We have computers now, and I will add that Aritra is at the bleeding edge with a great company over there whose name escapes me, but he's doing work on quantum computing, sequencing the genome.
Wow.
Because what you can remember, a quantum computer performs these calculations in superposition. So instead of being on and off, it's in these many infinite number of superpositions that we can address. So it means that our computations are mind-boggling and they can be done exponentially rather than linearly, which our current computers, no matter how fast they are, compute. So any other questions?
I have a question about the experiment that you were talking about at the end.
Yeah.
So you say that in the Wigner's friend, like let's say Bob and Bob's friend might not agree on what they see, right? So that's about, let's say, collapsing one particular photon. But do they agree on the statistics of it, like the wave function, the probability distribution that both of them see?
Great question. I know what you're saying. Look, I'll have to give you my own answer rather than the definitive answer, because I can't say I've read it anywhere, but I would almost definitely say the overall probability would still be 50-50.
Okay.
Because that's the way quantum physics works. The collapse has a 50% of being 0 or 1. So they would have disagreed, and I might mention there were 640 outcomes. It is in the, if you look at the references and the actual papers in there, and it's the important thing is it violated Bell's inequality. So that means statistically, it really was different. But overall, the probability balance, I would say, would be the same and would be, very close, depending on the sample, very close to 50%. Rather like when you collapse a qubit on the IBM quantum computer, if you do it once, you'll be near 50-50, or actually, if you did it 100 times, which is nowhere near enough, you would be near 50-50, but there would be a difference. And then you've got noise and decoherence and all of that. By the way, what is your company again, Aritra?
It's QB. It's still being set up.
Yeah, yes.
But yeah, I'm more into Q-Tech, like the company at Delft. It's like a collaboration between the TU Delft and the TNO company
That's
at Netherlands.
fantastic. I'm really pleased to hear that. The QB, the owner, founder, whatever he calls himself, Kern, I can't remember his surname.
Yeah, Koen Bertels. Yeah,
Kern
he is right now in
Bertels.
Portugal. Yeah, setting
Yeah,
it up.
Kern and I did a presentation together on sequencing the genome. Well, it must be about a month ago now, Eritrea, I guess. Eritrea is doing the clever work in the background, as is Cohen as well, and doing amazing stuff. And the only way we're going to get, and Eritrea won't agree with me here, or you'll say I'm exaggerating, but the only way we're going to get a vaccine for like COVID-19 is to be able to simulate what's called the ligand and the virus molecule itself, be able to simulate it for exponentially as we can with a quantum computer. At the moment, with classical computers, it's like looking at a movie for the first 3 minutes and then someone saying, what's the entire movie about? So you can have a guess, and that's where our vaccines come from at the moment. So that's why vaccines will work for some people, but they won't for others. In some cases, they have negative results. So I often say to these people who say, oh, vaccines, killed my daughter and all that, I say, well, hold on a minute. No one's saying they're perfect, but hopefully QB will be able to come up with the first quantum sequencing the genome, which means that we can have personalized, and this is what it's all about, personalized medicine. Do you want to add something to that, Eritrea? Or?
Well, it's still early stage, but we are progressing quite well. Like we have algorithms which we can provably demonstrate speed up over classical computers. Yeah, we need much bigger quantum computers to run them.
Yeah, you need pure
physicists
ones.
are doing a great job doing that. Like it's a lot of cutting edge research, both from the genomic side as well as quantum. Hopefully we'll converge sometime in the future, and then we'll have a much better world with lots of different applications.
Oh, well, here to that. Thank you very much. And Jaleh, I think you were on the IBM Qiskit course. Well, Eritrea is one of the best Qiskit algorithm makers, in the world. So he's doing Qiskit.
Right.
Yeah, you two should contact each other as well. Sure. And we can do that easily, swap things. Any other questions from anyone?
Not from me, thank you.
Yeah, thank you.
Okay, Kristen, are you okay?
Yeah, I'm great. Yeah,
I know you're great.
No questions. No, I understand it all perfectly.
Oh, yeah.
Clear as, yeah.
I was about to say how much of that could you follow, but I'm sure, Kristen.
I liked the bit at the end the best.
Yes, the almost proof we have that there were more that you create your own reality, which is something you've been saying for God knows how many years.
That's my jam. Yeah. Yeah.
So I think it's good knowing this stuff. Yeah, look, for everybody else's knowledge, Kristen and I go back a year or so now where I did presentations to the spiritual community, talking about collapsing of the wave function, and Kristen's all over and loved it, and her enthusiasm was fantastic. And if any of you are spiritual, Kristen has your own classes or something, don't you, in it, something like that?
No, not quite. I created some, in collaboration with you kind of as well, some audios and stuff where I was bridging the gap between
Yes.
spirituality and science. Yeah.
Yeah,
So
wonderful, wonderful stuff. And
it's coming. Yeah.
I can feel your enthusiasm from here. She's
Just
so
waiting for
much
that
fun.
last little bit. It's like, yes.
Yes, indeed. I'm a bit of a rare breed because I am very scientific, but I'm not going to discount someone who has a solution that differs from mine, especially when we don't know the solution. So we don't know the observer effect. We don't know the measurement problem. We don't know where these things are happening. And we have to admit the spiritualists and religions, I'm thinking of Buddhism, all of the religions basically, they have been saying this for years, that they can feel energy, frequency at a subatomic level, that they can collapse, they can project consciousness and collapse these things, and they can have out-of-body experiences. Now, I don't believe that in the classical world, so I just want to make that clear, but it's as valid as anything I can come up with. So there we
All
go.
things are possible.
All things are possible.
It's all out on the table.
Yeah, well,
Anyone's game, right?
And the reason why I wanted to present to the spiritual community is that it is all out on the table. It is science and spirituality and the Buddhism and that sort of thing. We should be talking with more respect for each other's standpoint, instead of always reaching that conflict stage where either party says, "Oh, you're talking absolute garbage," you know. And we have to stop there and we have to say, what is happening? And accept, the science world needs to possibly accept that we can't always prove these things.
Yeah.
It's very difficult
That's
to
the
prove.
gap.
That is the gap. Well said. And then, it was me who said it, not you. But you know what I mean? Well said. And well, yeah, it's, you know, some of these things can't be proven. Yet maybe they can be experienced because something's collapsing the wave function, Erythra. Something's collapsing the wave function, and something's doing it at a certain point of time. And I tell you what, if John von Neumann says it's consciousness, I'm not going to, you know, say it's rubbish. When a mind like his, which doubles Einstein's, when he says anything, you stand up and listen. Although I will say, the general scientific view at the moment, they're in the minority saying consciousness is involved. And a little bit of Wigner's friend, and a little bit, because remember, in the final experiment, which is called the Harriet's Watt from the University of Edinburgh, it wasn't done with consciousness. It was done with photons. Now you can say, one, is that a real measurement? And then you can say, yeah, well, you can say anything.
I'll just add that
add
a little bit to it.
Saved by the bell.
Yeah, so you're talking about the experiment being done with photons, but there is quite a famous paper which says that if human mind is conscious, so is an electron. So
yes.
So there are a lot of clues that do come from this philosophical and spiritual discussions into physics, and I think we should all like keep an open mind and not just dismiss them just because they cannot be proven, because that they lead to different thought directions and thought experiments. Even like Wigner's friend started out as a thought experiment, like, and then after so many years we are able to design an experiment that can confirm it. So yeah, it's really interesting to even take clues from all these different kind of discussions and think of ways which like can describe reality in a better way.
Yeah.
Beautifully said, and I couldn't agree more. I was about to say, you know, when I was saying about the photons measuring photons, it could be one, that a measurement hasn't taken place, or it could be that the photon's conscious.
Yeah, we don't even know what the definition of
know.
consciousness is. So
no, we don't. Aristotle said 2,000 years ago, the last thing the humans will ever understand is consciousness. And 2,000 years later, we know precious little more than he knew. So yes, it's just as conceivable that a photon somehow has consciousness. It's weird, but there again, everything in quantum physics is weird. So I think Arita's totally correct, saying, you know, let's all keep an open mind, because that's when you learn things. You don't learn things when your mind is closed.
No.
Yeah.
Okay, everyone. Well, look, that's been that's fine. Yeah, hour and 10 minutes of your time. So look, great to be with you. I'm doing a bit of a different thing every week. So I'll be in touch with you all, and please do, I think you've all got my email. Jaleh, you?
Yes, I've got your email.
Yeah. So feel free to email me. Let's have a chat, and let's see where it all ends up, because I'm talking to some, I might add, I'm talking to some very large corporations now about this stuff. Arita was quite right to say that we're all a long way from producing anything, simply because a quantum computer is so difficult to get a pure qubit. But there are things like QAOA. I don't know whether you're familiar with QAOA, but that's something that can be used now on a NISC, so it's a noisy intermediate quantum computer, to do amazing things like quantum optimization, etc., etc. Arita, are you involved with QAOA at all?
Yeah, I was almost spent an entire year writing QAOA algorithms.
You are just wonderful.
For genomics.
Arita is my hero, everybody, by the way. So, look, we have to have, I know we haven't had a chat for a month or so. You and I have to sit down, and I'd love to listen to you talk about QAOA, because funnily enough, I've got a few things I want to be doing with QAOA. So I find it difficult to understand it, and I find Qiskit difficult. Yeah, it's all helping each other, but I certainly would appreciate, and I think, in fact, I'll ask you, I won't embarrass you in front of everybody, but if you wanted to give a bit of a talk on QAOA next week or the week after or whenever, I know you're very busy, but I'd be very, very happy to facilitate that. And I know you would get a good audience.
I can just give a very introductory talk on what variational algorithms is about.
That's all we want. And Jaleh's nodding her head furiously.
Yes.
Yes.
First introductory, then.
Yes. Yeah, I mean, I read the whole, well, not the whole, but I read a fair bit. And you would have done too, Jaleh, in the summer school on QAOA. And I just thought, this is fantastic stuff, but I don't seem to be able to put it all together to know what to do. But I won't give away names, but a large corporate has contacted me about QAOA and optimizing freight packages, because the thing it does, Arita, is it solves the knapsack problem, doesn't it?
Yeah, it can be modeled to solve any hard problems as such, like approximate the solution for a hard problem.
Yes. And is this a little bit getting into P versus NP?
So you can always approximate an NP problem, like traveling salesman, knapsack.
Yes.
There are a lot of real world problems, even protein folding. So it requires solving very hard problems that you cannot exhaustively solve and find the perfect answer. But most of these cases, you are quite good with the approximate solution. So that's where you can use QAOA to get a good enough solution for your application.
Yeah, I understand that, and I've read that to be the case. So is QAOA just one algorithm, or is it?
It's more like
it?
class. It's like when you are writing a normal quantum algorithm, you just tell it to do a step after another. Think of QAOA more like a neural network, where you don't explicitly program it to do something, but every time you give it a feedback that you are this much percentage closer to the solution. So maybe you can try tweaking it a different way and try a different direction so that you're closer to the solution. So every time you are kind of have a feedback on the quantum circuit, that takes you towards the solution. You might not reach the exact solution, but it gives you, it kind of has a theoretical guarantee that you will reach close enough to a good enough solution.
Fantastic. Wow, I love it. We're going to have to talk more. I'll speak to you offline because I don't want to, in fact, and your friend, I can't remember, what we're going to have the presentation with your friend. What was that about?
Which one?
I put it to you that we should do a presentation on something, and you gave...
Yeah, Savas?
I can't remember his name.
It's about the fuel cells, hydrogen fuel cells.
Oh, okay. So it's all the same sort of related thing. Okay, look, I won't keep you all any longer. It's 8:15. Thank you very much for your attendance. Keep in touch, and it's a wonderful world. See you.
See you.
Bye.
Bye.